Hello, our new topic is design of composite parts. Now we have seen how the direction of the fiber affects the effective properties, stiffness of the composite materials, how the shear and normal stresses are coupled, and what are the consequences of off-axis orientation of the fibers. And then we have seen the fracture, so the failure criteria for composite materials. In fact, we are designing parts and we use these theories in order to predict their behavior. So why we use composites? Because of their lightweights and high toughness generally. So they have very high strength to density ratio, so specific strength, specific stiffness is high. On the other hand, their toughness, fracture toughness, so resistance to the crack propagation is very high. When we look at the metallic materials which we use, we see that their rupture stresses decreases with the frequency of the applied load. So if you have a cycling loading, for example, and you continuously apply the load again and again, you see that some micro cracks eventually grows and load bearing capability of the structure decreases. On the other hand, in composite materials, we see that more or less the rupture stress constant and independent of number of the cycles that are applied. Okay, so this is why we prefer composite materials in general. So let's compare the composite materials with the other materials and where we are. So this is one thing that we have to pay attention. In fact, the first line is the density. So we have the wood, and the density of the wood varies from 100 to more or less 1000, let's say. And majority of the composites and thermoplastics are between 1000 to more or less 2000 almost. So just think that, for example, high density polyethylene, it is 960 kilogram per meter cube. That's the density, whereas the PMMA, polymetal methacrylate, or we know it by its trade name plexiglass, so it is 1160 kilogram per meter cube, whereas the aluminum has a density of 2760 at around. We had titanium at around 5000 kilogram per meter cube, and steel at around 7000, 8000, and gold, for example, 10,000. Okay, so these are the densities of the materials. How about the tensile strength? So the tensile strength of the concrete is very low. We know that concrete cannot withstand to tensile force, so it is at around 10 megapascals, whereas the wood is a little bit higher. We know that it's it has an anisotropic microstructure, in fact. Then we have the light alloys, so between 100 and 1000. Then we have the steels at around 1000, that is the tensile strength of a steel. And when we look at the thermoplastics, in fact, the thermoplastics have very low tensile strength, whereas we use composites, so some reinforcing agent, to increase the strength of these thermoplastics, and then we cover more or less majority of the light alloys and steels by means of strength. So we cover this range. basically we can use the composite materials instead of steels and light alloys when the strength is critical. Okay, how about the stiffness or modulus of elasticity? Remember that modulus of elasticity is a measure for resistance to the deformation. So therefore the geometry of the structure after the applied load, after we apply the load, is also critical. So we look something in place of metals, so steels and other metallic alloys. So modulus of elasticity shall be comparable if you want to use the composite materials in place of those materials. So the thermoplastics range in few gigapascals, so more or less 4 gigapascal, 5 gigapascals, 1 gigapascal, and so on. So wood has a little bit of higher modulus of elasticity or Young modulus. So let's say 7-8 gigapascals. Then we have the concrete. Okay, so 30-40 gigapascals. Aluminum, so it is 70 to 100 gigapascals at around. Then we have the titanium at around a little bit more higher than aluminum, and moreover the steel. We know that the steel has the modulus of elasticity of 200 gigapascals, and if you look at the composites, certainly you can play with the effective properties or modulus of elasticity by changing the amount of reinforcing agent. Therefore you can use a composite material instead of steel, titanium, aluminum, concrete and wood in many places. So we are designing a part. In fact, how about the price? Because the cost is another criteria for us. So if you look at the cost, so steels, aluminum and thermoplastics has a cost of at around $2, roughly speaking. I mean, maybe the cheapest one is at that price, but generally, for example, the stainless steel has a price of $5-6 per kilogram. Identically, the aluminum has that price. Titanium is more expensive than that. In fact, it is like $50-60 or $100 depending on the quality. More, and on the other hand, composites are really expensive. So beginning from $5-6 and it goes up. So the cheapest composite material is glass reinforced polyester. In fact, so there is a trade between the cost and weight, strength and stiffness, let's say, in case of a composite. Therefore we want to design something that is cheap, okay, which means that we want to use less amount of material by means of composites. On the other hand, modulus of elasticity shall be comparable with the classical conventional materials that we use, or traditional materials that we use in engineering design, and also the strength has to be comparable. In fact, composite materials satisfy these conditions. Okay, so let's look at the material from a different point of view. So specific modulus and specific strength. So what is specific modulus? So modulus of elasticity per unit density of the material is called specific modulus, and specific strength is the strength per unit density. Okay, if you look at the materials, so the aluminum alloys have very low specific modulus. So you see it is like this. If we put on a scale, and more or less the strength is also very low. If you look at the E-glass, okay, so the specific modulus is comparable with the aluminum. Therefore we can use the E-glass reinforced composite material or E-glass instead of aluminum alloys. Certainly we are using a percentage effect. So on the other hand, specific strength is much higher in case of an E-glass. Kevlar is another fiber material which we use. It has much specific specific modulus, approximately 3-4 times. Moreover, strength is almost twice the E-glass, or more or less we can say that 8 to 9 times when compared to the aluminum alloy. So high strength carbon is another one that we use which we use as a reinforcing agent. In fact, it is higher than the Kevlar, so it is much more stiff compared to the Kevlar and E-glass, and also aluminum. And on the other hand, strength is comparable with the Kevlar. We have high modulus carbon. As you see, it has very high stiffness to density ratio. So in a very light structure, so what it means is you can have a very light structure which has very high stiffness. So this is why, for example, carbon fiber is commonly used in bicycle frames, and also their carbon has very high strength values. Okay, we have another fiber material which is boron. It has less specific modulus and lower specific strength compared to the carbon and maybe Kevlar, but we know that it is high. It has a high. It can withstand to high temperatures, extreme temperatures. Okay, now of course material is not the only thing that we use. So one of the things that we choose at the beginning of the design, but there are other things also which affects the choice of the material and other things. Also the loading is one of those. Certainly in many of our design we use a safety factor or design factors. The type of load that we expect to see on the design is also a parameter plays a critical role in our designs. So we may have static loading, for example. So what is static? So you apply a load and it doesn't change. So you just think that you have a bar made of composite material, a beam, and you put a weight on it. You hang the weight with the composite material, so it remains there. So the load doesn't change in time. If the load will stay for a short time there, so it will not, it doesn't need to withstand that load for a very long time, for example for years, then you can take the safety factor or design factor as 2. In fact, in case of a long duration, so short and long is a relative, has a relative definition here. So you can use the design factor as 4. So intermittent loading over long term. So what is intermittent load? So you apply a load and you take it back, and from time to time you do it. Again, it is relative. Anyway, you use the design factor as 4. In case of a cyclic loading, so you have a structure, for example, vibrating beam, which is what can be that one? For example, a shaft made of a composite material, so it rotates. Certainly there is some imbalance on the structure, and in fact this causes some harmonic loading on the structure. Then this is a suggestion. In fact, you should take the design factor as 5. If we have impact loading, also impact loading is an intensive load. Just think that you have a hard steel sphere and you throw the hard steel sphere to a composite plate. In fact, you have a very short duration of contact. So suddenly you throw it, in fact it makes a contact with the composite part, it deforms, so both deform, and then the steel sphere detaches. So it changes the direction of it changes its direction, and we know that the acceleration is basically the change of velocity. In fact, this means that you have a very high, since suddenly the velocity is reversed, which causes very high acceleration. And we know that according to the second law of motion, force is equal to mass times acceleration. This basically means that at a very short time you have a very high force in a very short time. So this is what the impact loading is. In that case, you should take the design factor as 10. Of course, for high performance composites, which are used generally in aerospace industry, we need lighter structure, because taking the safety factor higher might be safe, but in fact sometimes we need some weight saving, and in that case we have to be critical. The weight is critical, and therefore you choose the design factor as 1.3, 1.8. So it's very low. This is just an experience. So choosing the right design factor is just due to the experience. Okay, so we have seen the failure and how the stiffness changes with the fiber direction. Of course, we know that a composite ply carry more load in the direction of the fibers. So we generally prefer that the load is acting in the direction of the fibers. This is what we want, in fact. Therefore, we need to know, when we design a part, we need to know the loading condition at a particular location in order to choose the direction of the fibers. Okay, so what if we load the structure in the transverse direction? Certainly we know that the interfaces are generally the weak, depending on the structure. Perhaps, maybe there will be a debonding between the fiber and the matrix, or directly the matrix failure will occur, generally because the matrix material is not capable of carrying high level of loads. Okay, we can apply a shear load also. Again, we know that when you have a shear load, certainly you have stress, tensile stress in this direction, and the compressive stress perpendicular to it. When you have a pure shear as is seen in the figure, therefore you see a failure in the matrix again, so the rupture. So basically this is how we can interpret it. So just think that you have a pure shear case as is seen in the figure, and if you draw the Mohr circle of this unit element, so you have only shear stresses, right, minus tau and tau. Therefore principal stresses are sigma 1 and sigma 2, and they are equal. More or less in one direction it is negative, and in the other direction it is positive. And we know that basically what we do is we rotate the unit element in order to find the directions at which the shear stress is 0, and for this configuration it is 45 degrees, and certainly you have a tensile stress in this direction and you have a compressive stress in this direction. In fact, what you expect to see is there will be a failure in the matrix phase, because we know that in the perpendicular direction fibers are not capable of carrying the load, and mainly the matrix carries the majority of the load, and therefore it will not be able to withstand this stress. Okay, so we know that this is bad. This is not the thing that we want. So what is the solution? In fact, the better solution is to use one positive 45 and the one minus 45 degrees oriented plies. Therefore the structure will be capable of withstanding the stresses in both directions. So while the negative 45 degrees oriented fibers are carrying the compressive load, the positive 45 degrees fibers will carry the tensile stress acting on the unit element. We may have different orientations. Of course, there are different types. We generally use different orientations for the direction of the fibers in a laminate, and we have discussed the effects of orientation on the laminate's effective properties. We may have 90-degree oriented fibers. This is a general convention. We may have positive 45 oriented fibers. We may have 0-degree oriented fibers, minus 45, and again 90 degrees. In fact, we generally want to use symmetric configurations, and due to the coupling between the shear stresses and the normal shear strains and normal stresses, which causes warping and twisting, we prefer to use off-axis oriented plies close to the center of the laminate, and the others towards the upper surface or bottom surface of the laminate. So you can use either 90-degree oriented ply at the top or 0-degree oriented ply at the top, depending on your design and on number of the plies and configuration that you or properties that you want to attain. Okay, we have seen how to show the configuration of a laminate. Generally, we prefer symmetric and balanced laminates. So remember that when you have a positive 45 degrees ply, there should be equal number of plies in the other direction, so a negative 45, in order to balance the warping caused by these plies, and it should be as close as possible to the center in order to avoid residual stress-like effects because of the coupling between the shear or internal stresses, in order to avoid the internal stresses, let's say. For example, here we see a laminate with the 7 plies. So certainly the fourth one is the mid plane. It is symmetric because we have 190 degree ply, and 2 minus 45 degrees plies, and 2 positive 45 degrees plies. And since we have 2 0 degrees plies, we put these 0 degrees to the lower and upper surface of the laminate, and we show it like this. So we have 0, 45, minus 45, 90, 90 is the center, and we say that it is symmetric. This is how we show it, conventional notation. In case of a symbol, this is how we show it. We show the directions. So we have 1 90 degree, 2 positive 45, 2 negative 45. We have 7 plies and 2 0 degree plies, and the 0 degree plies is the 28% of the total plies. So we can easily find the percentage of the other plies from this expression, because total has to be the 100. Okay, so we have already talked about some properties. So why we need to use symmetric configurations? Remember that we polymerize, or we the material, the matrix material. Matrix material is generally a liquid-like, has a liquid-like behavior, in fact. And during the polymerization, there exists a chemical reaction which we call curing, and in fact it generates heat. Therefore, when the temperature is high in the initial stages of the curing, it's okay, but when the temperature decreases to the room temperature or the ambient temperature, we see that due to the mismatch of the thermal expansion coefficient between the layers, we see twisting or warping if there is no mid-plane symmetry. But in fact, if we have a symmetric structure, so we know that it is okay at high temperatures, but when the temperature decreases, certainly the structure will preserve its shape. So there will not be internal stresses, residual stresses, due to the mismatch of thermal expansion coefficient. You can think this like this. I mean, you have, remember that you have an aluminum and steel beams, and they are perfectly bonded one on the other. So when you heat them, certainly this beam will be bended in one direction. In fact, if you sandwich the aluminum layer between two steel ones, because they want to elongate together, and certainly they will not be able to elongate together, and they will bend to one side. If you sandwich the aluminum one into two steels, so one steel will try to bend the structure to the one side, and the other one will try to bend the aluminum to the other side, to the opposite side in fact, and as a result these two will compensate, the deformations of these two will be compensated, and they will elongate it only in the direction of the beam. So this is how we can interpret this effect. Okay. So there are other designations in fact. So one is you can show the direction of the fabric. So sometimes we buy the composite by means of as preprex. So preprex comes as a resin impregnated fiber material. So we have, for example, we may have one layer of balanced fabric which has fibers in both directions, one on 0 and 90 degrees, and in fact we may have one layer of again balanced fabric which has direction of positive 45 and negative 45, and again another layer of balanced fabric. So this is the mid plane. So this is how we can interpret it. So let's look at it, each symbol independently. Certainly when you have 0 and 90 degree oriented fibers, or in the longitudinal and transverse direction, this is what we have. We have 50%, we have a ply with a 50% in the direction, in the x direction, and 50% in the y direction perpendicular to it. Then we may have a ply with fibers which are not oriented with the x or y direction, or plus 45 or minus 45. Then we have 50% of positive and 50% of negative, and then again we have another one which is oriented in the other direction. So certainly the final configuration will have the percentage like this. So 33% of the fibers or the plies will be oriented in the 90 degrees, 17% will be oriented in the 17 degrees, and 33% will be oriented in the 0 degrees, and 17% will be oriented in minus 45 degrees in our laminate. Okay, so we are designing a laminate, and certainly we may need to. So first of all, weight saving is an important criteria, one of the most important factor in using the composite materials, because they are very expensive. So we may not need to use same amount of same number of plies in every region of our design. Let's say that because of the load bearing capability, so what we do is first we determine the number of the loads, the extent. We know, for example, external load, And in fact, if you know the external load from there, which means that you know the resultant forces per thickness, in fact you have already chosen the material, which means that you know the stiffness, and certainly you have a design criteria for the deformation, and you are just trying to approximate the thickness of the laminate. And after the calculation, let's say that you find that in certain regions you need a different thickness, and in certain regions you need let's say lower thickness, and in certain region you need a higher thickness, which means that there has to be a gradual change between the number of the plies. In that case, what you do is like this. So in every 6 millimeters you decrease 2 plies generally. Again, I'm saying that it's generally because you cannot exactly say that this is the rule of the thumb. So you made the calculation and you see that you need a 16 ply with 2 plies in the y direction or 90 degrees, and 4 plies in positive 45, 6 plies in the 0 degrees, and 4 plies in negative 45 degrees. So we have this configuration basically 0 plus minus 45, 0, 90, and plus minus 45, and then 0. Okay, and you want to decrease the number of plies. In fact, first thing that you do is you suppress the 8 and 9. So remember that this is your center. So first you begin to exclude the plies close to the center. So first this is symmetric, so 1, 2, 3, 4, 5, 6, 8, 9, 10. Okay. Okay, so this is your center. Just a moment. 0, 1, 2, 3, 4. Okay. And 90, and then there is another one. 90, okay. So first you take the 8th and 9th ply. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then there is another one. So first you take out the 0 plies, 0 degree plies from the laminate, and then the next one is the 7th and 10th. So 1, 2, 3, 4, 5, 6, 7. So you take out the 0 degrees. In fact, then you take the minus 45, and then next the plus 45 degree plies from the laminate, and in fact you gradually decrease to 10 number of plies in order to reach the final thickness. For example, in this case it is 1.3 millimeters here, and here the thickness is 2.08 millimeters. Okay, so let's see how we can place the fabrics. Of course, we talk about the direction of the fibers and effect of direction of the fibers on mechanical properties, and let's see how we can place the fabrics in general. Mainly we have parts with complex shapes, which means that we need to adjust the direction of the fiber or the fabrics according to the given shape. Certainly the fabrics are sent to us in certain shapes. So we have 1 meter, 2 meter width of and maybe 10 meters long. So if you have a rectangular shape, for example, with some loading, certainly this is the good. So the first figure is the good placement of the fabric, and in fact, because we cut the shape and we orient the fabric in a manner that we don't shorten the fibers. So these are the direction of the fibers. So fibers are all along the part, and the dark black lines are the cuts. If you have an L-shaped geometry, of course this is the good placement of the fabric. Moreover, we can place the fabric like this. So these are the orientations of the fibers, and as you see, these dark black lines are the places of the cuts. So what is the disadvantage? Why this geometry is bad and why this is better or good, in other words? Now we mainly infiltrate the spaces with the matrix material, and this basically means that the fibers has a certain length shortened. In fact, the ends of the fiber do not carry load or much load. So this is basically placement of the fabric like this means that you decrease the load bearing capability of the structure. In fact, it is the same in this placement of the fabric. Certainly the ends will not carry too much load, and as a result you decrease the load bearing capability. You possibly see the failure here and also see the failure here, because we know that the matrix is capable of carrying less loads. Other problem that we face with is the corners. Now we have the fabric and we cover the fabric with the resin. In fact, it is not possible to have a sharp corner. This basically means that we are going to have spaces at the sharp corners, as you see in the figures. So what to do is we prepare a shim and we put there in order to avoid the deformation of the laminate and cause a failure there. So we use a backing material. So we use a preformed geometry there. Okay. Now we manufacture the laminate, that's okay, but in many cases we need to join it with some other parts, or we need to join different laminates to in order to produce, or in order to have a certain product. So let's see the advantages, or let's see how we can handle such kind of a problem. In fact, having a hole means that there will be a deficiency in the degrees in load bearing capability of the structure, and we need to evaluate it. Possibly the hole behaves like a crack, and as a result we have high stresses around the crack. In fact, we may have different types of failure. Generally we have a laminar with fibers which have different orientations, and commonly 0 degrees, 90 degrees, positive 45 and minus 45 degrees laminates applies, in fact. So we may have vertical failure lines, so cracks on the surface. This basically means that we have the failure in the matrix. So the 90-degree ply fails. So load bearing capability of the 90-degree ply is not sufficient. So this basically means that we need to add some more 90-degree ply, increase the thickness. What if we have 45 degrees failure patterns? This means that 45 and minus 45 degree oriented plies with positive 45 and minus 40, negative 45 degree fibers fails. We have a matrix failure in those plies. So we need to increase the number of those plies in that case. We may have 0 degree failure, in fact. So then, which means that we have lines in the direction of the force. So this figure is a little bit not correct, in fact. So what if we have a delamination in case we see a color change? So this is what we are going to see in case of a delamination, and certainly we see the other failure patterns on the surface because of the matrix failure in the other plies. This is what we expect to see. So why it happens? That is the question. Now, in case of a metallic material, if you apply a tensile stress, certainly you see that there exists a stress concentration around the hole, and in fact there is a certain region at which the stress exceeds the yield stress, and as a result you see a yielding. But in the case of a composite material, you don't see it. You see because it doesn't possess any yield deformation, so it fails immediately. In generally, the epoxy, for example, is a brittle material. In fact, many of the fiber materials are brittle as well. So you see a sharp increase around the hole. This is the stress distribution. In fact, this results in certain stress concentration around the hole. Therefore, it is important to know how to place the holes in a laminate. So let's look at the holes. You may have different you can place the holes in different manner. The holes are important because we use them for bolted joints and riveted joints. In fact, in this figure we see the weakened zone. So the dark brown, darker zones are the weaker zones. So as the color gets darkened, so it's more weaker. So we see that these regions are weaker in this configuration if you put the hole side by side, and as a result you see a high stress value around the holes. If you put the one hole in front of the other, then you see higher stress value in front of the hole, which comes from the joint. It's a pin, it's a rivet, or so whatever it is. Moreover, even though in the zones next to this zone the stress is higher, still you make the design with respect to this area, and in fact you have much lower stresses in this region on either side of the hole. As a result, this type of design is preferred compared to this type of design, because load bearing capability of this design is much higher compared to this one. So we unlikely see a failure here or here. So let's look at the failure types of the bolted joints. In fact, here we see a double lap joint, bolted joint. So you may see a failure in the center laminate. So the tensile, this is a tensile fracture. Basically, the number of plies in the direction of the load is not sufficient. This is what it means, simply. And you may see a failure at the top of the at the upper or lower plate. In fact, this means that the shear dominates the failure, and in fact we know that the shear generally is carried by the off-axis oriented plies with the off-axis oriented fibers. So you need to increase the positive 45 or minus negative 45 degree plies, number of plies as well. Bearing failure. So as you see that the hole is elongated somehow, so which means that the fiber matrix delamination, matrix debonding, and in fact this means that the thickness has to be increased in this case, because hole is not capable of carrying the applied load. And finally, both tensile and normal fracture, so the thickness is not sufficient in general for this type of design. Okay, so we have bolts. In fact, at the joint we may see fracture of the bolt or rupture of the laminate. So why it happens? So this is one of the important points, and how we can avoid such kind of failures. This is next thing. In fact, the distance between the holes or joints plays an important role, so we have to decide it. Now, in the placement of the holes, there are certain we can put some certain rules. Actually, these rules are not must, they depend on the experience. So the pitch, the distance between the centers of the holes shall be between 4 times the diameter and 6 times the diameter, and distance to the free edge shall be 6 times the diameter. Approximately, these are approximate values, must be larger than, of course. The thickness must be minimum equal to the radius, thickness of the laminate in that region. Generally, the stress around the hole is not in one direction. Even though you apply a tensile load, you have a complex state of stress around the hole. As a result, you need off-axis, you need fibers which are oriented in off-axis, so it can be positive 45, negative 45, or in some other directions, and mainly the safety factor or design factor shall be bigger than 2. We may bond the, you may fix the, you may create a joint with a metal material and the laminate. In fact, you transfer the load from laminate to the metal or metal to the laminate, and generally you may have different configurations for the fiber orientation, and you determine the design. But in fact, how we can calculate the stresses in the composite material, so that is one of the important points, because we will basically design the joint region according to these stresses. Now let's say that E is the thickness of the laminate, so this is the cross section. We have the metal here. S is the area of this small region which is next to the hole, and we have a complex loading. We have the shear force and normal force, and basically the bearing strength must be smaller than the diameter multiplied by the thickness, because otherwise the structure will fail. But how we can calculate the normal stress? So this means that around the hole stress increases, and we need to make an approximation for this increased stress. So first of all, stress in this area, the average stress in this region is force divided by the area. So this is the point where we see higher stresses, because the area is smaller and the total force will be carried by this area in this region. That is the average stress. And moreover, we have a stress which is increased due to the geometry. So we approximate it by force divided by the diameter multiplied by the thickness, and we take the 20% of the stress. So we basically have this area, but we don't have and we take the 20% of the stress, so we don't have a material there, and we just put a value there. And then we have the safety factor or design factor alpha. So for tension it is 0.6, and for compression it is 0.8. So we take a higher value for the compression, because the structure can withstand to higher compressive stresses in fact. So we need a lower increased stress value. In case of a shear, we calculate the shear stress, the average shear stress which is carried by this area, and then we divide it by 0.7. So these are just experienced dependent values. These numbers are okay. We may have different types of joints. In fact, the stresses around the holes are critical. We may have we may connect the metal part to the laminate, then the angle plays a role, and we put some shielding around the hole in order to distribute the force which comes from the pretension in the rivet, in order to avoid the stress concentration on the surface of the laminate. As you see, you may use different types of connections for this. In fact, one thing that you should do is, in the region of the rivet, the thickness has to be increased, because you know that the structure is weakened. Therefore, in order to carry the load, you need much higher thickness there. Okay. Other place that we use the joint or bolted joint is the sandwich structures. In fact, you may connect the sandwich structure to a metallic part, and generally the sandwich structure is subjected to a shear force and the bending moment. In cases of such kind of a bending moment, certainly this means that you have a force couple, and moreover, while one for example, in this type of loading where the upper laminate will be subjected to a compressive load, whereas the lower laminate will be subjected to a tension force. So this is one problem. Of course, the shear force has to be balanced. In this case, you see that this metal part will apply a force to the laminate, a concentrated load, and in fact this has to be avoided, or somehow the structure has to be designed according to these forces. Certainly the joint, the body of the bolt or rivet is subjected to shear and tension in this connection, and the stress on the laminate due to the pretension makes is non-uniform and has to be paid attention. So how to avoid it? We need to distribute the force which comes from the pretension and imbalance of the forces. So as a result, one approach is to put a metal just under the bolt, and therefore you distribute the force which comes from the pretension to the laminate to a larger area, so you decrease the stresses on the surface and you avoid the damage. This is a good design, and in fact putting the metal in between will not help, because you increase the bending moment, and in fact again the pretension due to the bolt is a major problem. So what else? We may have titanium or metallic plates which is fixed on the laminate, and therefore the laminate may be connected to the part through these metallic parts. This is what is desired. Of course, this is a good design. Certainly you have a uniform thickness in the laminate. In fact, this is one bad approach. Again, even if you increase the thickness, so this cut of the plies will be a problem because of the end effect, let's say. Other type of connection is bonding. So apart from the bolting and riveting, you may use bonding, and we may use different types of adhesives in order to bond the laminate to the other structures. What are those materials? Again, we use polymeric materials, epoxies, polyesters, polyurethanes, and methacrylates. So epoxy and polyurethane adhesives are used very often, and we are quite familiar with them. So epoxy you can find in a hardware shop. Again, it behaves similar to the epoxy resin. So basically you have the curing agent and you have the epoxy material. You add the curing agent to the epoxy and it cures. In the hardware they tell you that okay, you mix 1:1, but simply by playing the amount of curing agent you can play with the mechanical properties of the adhesive layer of the epoxy. So increasing the amount of curing agent will makes it harder, but less stronger, decreasing the amount of curing agent, will decrease the stiffness, so it will be elastic, the bond, in case of an epoxy. But on the other hand, it will be less strong, let's say, we can say that. In fact, the polyurethanes are the adhesives which we use commonly in automotive industry in many places. For example, fixing the window glasses onto the car, they use polyurethane adhesives. So what are the properties that we desire from the adhesives? So basically, they should withstand to high temperatures. In general, there are some high temperature adhesives which can withstand to 200, 300 Celsius. They should withstand to moisture, so their mechanical properties shall not degrade with the moisture, and they should withstand to many of the chemical agents, because in different parts of the industry, for example, the rain, the environmental, they will be subjected to some environmental effects, in fact, and you can use such adhesives or material in different places. Okay, so what are the things that we have to pay attention on the surface? First of all, the surface has to be clean and oil and dust free. So this is one thing that we should do on the adhesive surface. First of all, surface pickling shall be avoided. So the surface has to be rust free, smooth and clean in order to have a better adhesive strength. What are the other things that we have to pay attention? The thermal expansion coefficient of the adhesive layer has to be as close as possible to the bonding materials. So this is one thing that we should pay attention. Moreover, deformation under distress is an important factor, because if the deformation is large, this may induce failure of the adhesive bond. So what shall we what are the things that we have to pay attention in the designs? So just think that you have two laminate and you want to bond them together. So this is the thickness, and you put the bonding between them. This is a bad design because you have very small area, and the bond adhesive layer will be subjected to a tensile stress, and in fact this will cause a failure. Again, you may bend the laminate and try to increase the area. Of course, this will again is a bad design, because such kind of force will generate a tensile stress again, and moreover you will have some moment which generates a stress not only in this direction, but certainly you have complex state of stress, and as a result this design will fail immediately. So you may have single lap joint. This is certainly in this case you will have shear stress along with the normal stresses in the adhesive layer. This is a case sometimes we use it very often, even though it is a poor state of poor choice of the design for the adhesive layer. So what shall be done? Okay, so this is a good design. You put a metal bracket around the adhesive layer. Certainly the adhesive layer will be subjected to a compressive force, and in fact we know that the material will withstand higher compressive forces compared to the tensile forces. As a result, this will transmit the force much more better, and in fact this metal bracket will avoid the excessive deformation due to the stiffness of the adhesive layer. You may use double lap joint. In fact, double lap joint is a good because you preserve the symmetry, and as a result you have higher area and you transfer load in a much more better way, because you avoid the tension in the adhesive layer. Certainly you may have circular structures. Of course, in this case the adhesive layer is subject to the shear, but perhaps the adhesive layer will carry the whole load. Here in this case surface area is very small, therefore the adhesive layer may not be capable of carrying the whole torque applied. What you should do is you create a bend and you increase the bonding area and you decrease the stress in the adhesive layer. What else you should do? You should change the diameter. You increase the diameter gradually and you use the one adhesive layer here and you do another, for example, so you put tube in a tube. Basically one thing that you may do is you put a short tube and you satisfy, you put the adhesive in between. In this case you have an increased you increase the length of the adhesive layer, so not the thickness, and as a result you increase the adhesive area. This will decrease the stress. Other type of bonding is you may have a scarf joint. This is also a better design. So you have an inclined cut on the circular shaft. As a result of this increased length, you have a higher area for the adhesion. In fact, you can predict the stress, average stress in this case, applied force. If you apply a normal force, you apply force divided by cos alpha divided by length multiplied by the B. B is the thickness of the adhesive layer. Sorry, B is the thickness of the adhesive layer in this case. Sorry, the thickness of the laminate. I apologize. And then it has to be smaller than the rupture of the adhesive stress. Certainly you use a safety factor here as 5. We may have different types of joints. So you may have this type of joint, so the surfaces are parallel. You may have different types of this type of joint, this type of joint, so the surfaces shall be in parallel. In case of a you may have parallel surface of joints. Okay, so let's look at the stresses in the joints. Certainly the adhesive layer is subject to the complex state of stress, and we may have the adhesive layer may be subject to the normal stress sigma and the shear stress. Let's assume that we have 2 laminates, and assuming that the thicknesses the width of the laminate is 1, we may approximate the shear stress and normal stress acting on the adhesive layer. So basically, when we look at the normal stress, in fact we see that they make the maximum towards the free ends of the adhesive layer, and again the shear stress is 0 on these surfaces, and it makes a peak close to the this region, which means that we reach the maximum stress close to the ends, and possibly we see the failure in this region. So certainly the stress in this region must be smaller than the rupture stress. How we can calculate the approximate the shear stress? For example, if you have a normal stress in a joint, for example, you just think that you have the normal force coming to one laminate, it will generate a shear stress on the adhesive layer. We have some parameters, so the shear stress is alpha 1 divided by 2 multiplied by square root of alpha 1 and alpha 2. Alpha 1 and alpha 2 are function of the shear modulus of the adhesive layer. Young modulus of the laminate, in case of an alpha 1, it is Young modulus of the laminate 1, and then multiplied by the thickness of the laminate 1 multiplied by the thickness of the adhesive layer. In case of an alpha 2, it is Young modulus of the laminate 2 multiplied by thickness of the laminate 2 multiplied by the thickness of the adhesive layer. So you can approximate the shear stress caused by the normal force which comes to the laminate with this expression. Moreover, in case of a shear stress acting on the laminate, we can approximate the shear stress coming to the adhesive layer with this expression. So it is 3/4 multiplied by the thickness of the laminate 1, and it is independent of alpha 1 and alpha 2. And moreover, we can approximate the shear stress generated by the bending moment. In case of a bending moment, certainly the adhesive layer will try to elongate. Therefore, the Young modulus of the adhesive layer, adhesive material, is important. So we define two new parameters in this case. For that case, so beta 1 and beta 2. In fact, it also generates a shear stress. So the shear stress generated by the bending moment is equal to 3 alpha 1 divided by thickness of the first laminate multiplied by square root of alpha 1 and alpha 2 multiplied by bending moment. Now beta 1 and beta 2 is due to the tensile stresses in the adhesive layer. In fact, the length of the adhesive layer can be approximated by using this approximation. So alpha 1 plus alpha 2 multiplied by the length of the adhesive layer, square of the length of the adhesive layer, shall be greater than 9, whereas beta 1 plus beta 2 multiplied by length of the adhesive layer, fourth power of the length of the adhesive layer, must be bigger than 4 multiplied by 6 to the power 4. These are just empiric relations, in fact. Okay. Now we may have different types of again layers. So let's how we can predict the stress in the adhesive layer. First of all, we have flexural moment, bending moment. Bending moment is equal to force applied to the laminate multiplied by thicknesses, total thickness, average total thickness of the laminates plus the thickness of the adhesive layer. This is the normal stress, and from here we can approximate the shear stresses. Total shear stress is the shear stresses generated by the normal force plus shear stress generated by the bending moment for this configuration, and moreover the normal stress is, or tensile stress is generated by the stress generating by the bending moment. We may have tubular or cylindrical geometries. In fact, in that case, the stresses in the adhesive layer can be approximated by this expression. So it is maximum stress is 16 multiplied by the torque applied multiplied by the outer diameter of the inner diameter of the tube. Outer diameter of the tube. So phi prime is the outer diameter of the tube divided by the moment of inertia. So this is 16 comes from the moment of inertia, rotational moment of inertia. Basically, it has to be smaller than 0.2 multiplied by the rupture of the adhesive layer, because the total torque will be carried by this adhesive layer in this design, and 0.2 is the safety factor. We see the maximum shear in this region in case of this design. So we can predict the average shear stress with this expression. So it is 2 multiplied by applied by torque P to the inner diameter, outer diameter of the inner tube, square of the outer diameter of the inner tube, multiplied by length of the adhesive layer. Again, it has to be smaller than the rupture stress of the adhesive if we want to predict the maximum stress. Then you can use this expression. Of course, use of this expression is just a question mark, so we already have the safety factor. Okay, so let's see the orientation of the fibers in such kind of a circular shaft. So the first design, even though the rupture stress is between 5 megapascals and 10 megapascals, so when you apply such kind of a bonding, and if you put the ply which has a fiber orientation perpendicular to the loading to the outer surfaces, certainly you may possibly have a matrix fiber debonding, and you see a failure in the matrix. So this is a bad design, and certainly this is the right one is a good design, because the ply with the ply which has a fiber orientation in the direction of the force is located just next to the adhesive layer, and therefore no failure is expected here. How about the bonding of the sandwich panels? Now we have a honeycomb structure or the core material. In fact, you may have you may put a laminate or a metal to the end of the core material, and you may use an adhesive layer to fix it to the upper and lower laminates. You may have different types of ending. So you may you have this structure. You can use such an end. You can use this type of end, and you may use this type of end. So again, you have an adhesive layer. Generally, such structure is subject to the bending moment. So therefore, state of stress at the ends are complicated. Okay, so you may have such kind of a structure. So this is the right hand side is preferred compared to the left hand side, because when this laminate is subjected to a bending moment, for example, certainly this metal stop or metal end will try to resist its motion, and it will transfer the load to the bottom laminate. In this case, you have a debonding here, and in fact, as a result, you will have a failure, because this honeycomb structure and this part will try to apply a force on the core material, and certainly the core cannot withstand that force. This is again a bad design, because when the structure is subject to the bending moment here, certainly the upper laminate will exert a force on this inclined end, and as a result you will see possibly a debonding here, and the whole structure will fail. How about the other? Next one, this design is also not acceptable, because once you have a bending on either side, perhaps this sharp corner will begin to exert a force to the laminate. If this bond fails, because this is the first place that we expect to see a failure, once this bond fails, it will begin to apply a force to the upper laminate, and complete debonding from the core materials can be seen in either direction. So you may have such kind of a design. In fact, what we see is we have a metal part on either side. Possibly this may be done for the joint. In fact, we see that the struts of the honeycomb structure under the channel is buckled. So basically this means that they reach their they cannot deform more. Possibly they plastically they have a permanent deformation, and in fact when you apply a force from either side, it will not debond easily. This is again poor design, because once you apply a bending moment, you possibly have exert a force from here, and then you see a failure from this region. So this basically means that you will have a debonding here, and then it will continue and you will have debonding in the other part. So how we can improve such joint? You can use inserts. This is one thing that we can do. So in fact, first you distribute the force to the whole area, to the laminate, and you fill the space between the groove and core material with some composite materials, again particulate reinforced composite materials. This is one thing that you can do. In fact, you may have different you may use different types of designs. You see here in order to improve the joint. There may be some other types, in fact, and moreover you may use some other different types of bolts in order to distribute the force to the structure. Of course, we can use other types of inserts. If, in case of a, for example, you may have a part, composite part, which has to be pinned to somewhere, for example, and in fact, just imagine that you have a tensile force. So this is just subject to a tensile force. Therefore, you need just a unidirectional fibers. And you may use such kind of an insert. Since this insert so the sum of the forces has to be 0 because of the static equilibrium. Therefore, there will be a reaction force which comes to the insert in this direction to the right hand side because of this tensile load. And in fact, because of the curvature here, the stress will be distributed and you have a better design. This design is good. This is also acceptable. You can use such kind of a design here. So you have sharp V-type groove and you gradually change the thickness of the laminate from certain desired thickness to a lower one, and as a result the fibers will be subjected to a tensile force. Of course, when the force is reversed, so you have a compressive force, for example, it is not a good idea to use such an insert with a sharp corner. Certainly this will cause a delamination. What else? If the you can use such kind of a metal ring. Remember that such circular hole will generate a complex state of stress, and therefore the stress in front of the stress in this region is can exceed the rupture stress and certainly may fail. So this is not a good design. So you can use such kind of an insert for the alternating load, but in fact this is not a good idea because you may generate a debonding.